Hey folks, welcome to my channel number 10. So we have the problem on our screen. Determine whether the following function is differentiable at the indicated values. Mod of x square minus 1 at x equals 1, right? So my f of x equals mod of x square minus 1. And we know that my mod function is represented as, so my mod of x, if I take the basic mod function, my mod of x equals x for x greater than or equal to 0 and minus x for x lesser than 0, right? So if I'm going to do the same thing for the mod function that we have on our screen, all that I need to do is wherever I have x, I will have to replace the definition by an x square minus 1, right? So what do I get when I write this function? My mod of x becomes x square minus 1 whenever x square is greater than or equal to 1, right? So let's write the first part of the equation and let's understand what do we get, right? And this is when my x square is greater than or equal to 1, right? That, and then I have a minus of x square minus 1 whenever my x square is lesser than 1, right? So let's write that and let's spend a few minutes trying to understand how this function uh, will behave, right? So my x square minus 1, my f of x is x square minus 1 for x square greater than or equal to 1, right? So what do we mean by x square greater than or equal to 1, right? So whenever my x square is greater than or equal to 1, then my x will be greater than or equal to 1, right? Or because it is a square function, I also have my x can be lesser than or equal to minus 1, right? So what happens is, so let's say let's pick up x equals minus 3, which is a value which is lesser than minus 1, right? We see that when I substitute uh, minus 3 the whole square, then I have 9 minus 1, which is 8, and mod of 8 will be 8, right? So this function will be equal to x square minus 1 for all x square greater than or equal to 1. And when you say all x square greater than or equal to 1, then it also means my x is greater than or equal to 1, okay, in the positive domain, and my x is lesser than or equal to minus 1 in the negative domain, right? So that's how we write this equation. And when I move to my next function, right, which is minus of x square minus 1, which means I can write this as 1 minus x square. And when I write this as 1 minus x square, my x square lesser than 1, what does it actually mean? It means my x lies in the interval minus 1 to plus 1, right? So let's write that minus 1 lesser than x lesser than 1, right? So this is how we rewrite this equation. So I'm going to repeat this. So what happens is my f of x becomes x square minus 1 for x greater than or equal to 1 and for x lesser than or equal to minus 1. And I have 1 minus x square for x belonging to minus 1 to 1 open interval, right? So that is how we rewrite this function, and it's very important you understand this step before we proceed ahead, right? So now let's examine the differentiability at the point x equals 1, right? So we know that we will have to start off with our RHD. So let me write that. RHD is f dashed of x naught plus, which means I'm going to estimate the right hand derivative, and at x naught equals 1, I can comfortably replace my x naught with 1, right? So wherever I have x naught, I'm going to replace it with a 1 and then further do a substitution for f of 1 plus h and f of 1, right? So next we have our f of 1 plus h, right? And what is our f of 1 plus h? F of 1 plus h is when my x takes a value which is slightly less greater than 1 by an infinitesimal h, right? So which function do I have to pick up? I will have to pick up the function when x is greater than or equal to 1, right? So I will have to pick up x square minus 1 as the function to be substituted here. And what do I do with this? All that I do is wherever I have an x, I will have to replace it by a 1 plus h, right? So let me do that. So I will have 1 plus h the whole square when I write this, right? So let me write 1 plus h the whole square minus 1, first part of the numerator. And then I have my f of 1, right? What is my f of 1? Again, it is denoted by the function highlighted in yellow, which is 1 square minus 1, right? For x equal to 1, right? So I have a 0, right? So, and then I have a h in the bottom. So when I expand this, I get 1 plus h the whole square minus 1, right? And what is my 1 plus h the whole square? It is nothing but h square plus 2h plus 1, right? So let us rewrite that. And I have my h square plus 2h plus 1. And then I have a minus 1, minus 0 you can skip. This is what we are left with. So I can cancel out my 1 here, and I'm left with h square plus 2h divided by h, right? So after I cancel out my 1, this is what I'm left with, and I can still pull out a h, right? And remove the h from the denominator. So let's do that, and I'm left with a h into h plus 2. Yeah, and I can pull out my pencil and now cancel out my h and h, right? And I'm left with a h plus 2, which is not further available to simplify. And when I do a substitution, I'm left with 2, right? Right. So there we have our RHT. It is a finite number. So the RHT for this function does exist. Now let us jump to the LHD, right? So let me write down my LHD first. So my LHD is f dashed of x naught minus equals limit h tending to 0 f of x naught minus f of x naught divided by minus h, right? So my x naught is 1 because we are examining the differentiability of the function at x equals 1. So let me substitute my x naught with 1, and let's move to the next line. So my f of 1 minus h is when my x takes a value which is lesser than 1 by an infinitesimal h tending to 0, right? So which means I will have to apply the equation for x lesser than 1, right? Which means I will have to apply 1 minus x square, right? So wherever I have an x, I will have to replace it by a 1 minus x square. I'm sorry, wherever I have an x, I will have to replace it by 1 minus h in the equation 1 minus x squared. So let's do that. 1 minus 1 minus h the whole square, right? So that's the first part of the numerator. And then I have my second part, which is minus of f of 1, which we evaluated in our RHD, which will be a 0. So I'm going to skip that step because we can ignore f of 1 because it is a 0. And we are left with 1 minus h the whole square divided by minus h, right? So I can further expand this. And when I expand it, what do I get? 1 minus. What is my 1 minus h the whole square? It is nothing but 1 plus h square minus 2h. So this is what I get. And remember, folks, you have a negative sign in the denominator. Don't miss that out. And then when I further write this, I clearly see that my 1 and 1 gets cancelled. So I can comfortably pull out my, remove the 1, and I have minus of h square minus 2h in the numerator. And when I write that, I get 2h minus h square, right? So I get 2h minus h square divided by minus h, right? And like we did in our RHD, I can represent this as h into my numerator is 2 minus h. Basically, I'm pulling out one h, and then I have my minus h in the bottom. This is how we can represent this particular equation. I hope you are with me. All that I've done is I've pulled out h from the numerator. When I pull out h, my 2h minus h square becomes h into 2 minus h. And then I have my minus h in the denominator. I can cancel out my h and h, and I'm left with a negative sign in the denominator and 2 minus h in the numerator. So what does that mean? It means I can rewrite this equation as h minus 2, right? So I have my h and h cancelled out. I'm just repeating it, folks. My h and h gets cancelled out, and I have my minus sign. I have it as 2 minus h by minus 1, which means I'm left with h minus 2, which becomes as h tending to 0, I have it as minus 2, right? So this is my LHD. We see that my LHD is also finite. It does exist, but my RHD is 2 and my LHD is minus 2. Therefore, my LHD not equal to RHD, right? And therefore, the function is not differentiable at at x equals 1, right? So that's how we solve this problem. I hope you found this video useful. Please do subscribe to my channel and support. Thank you.